Hello and good evening. I'm Paul Wheels. Welcome to AIoTHub. We've got an absolutely awesome show with you with Pete this week. Bringing in John, Mr. Stavely. How are you, sir? What have you been up to?
Went away for half term down south, chasing up IoT speaker content. So please get in contact if you've got a talk idea.
For sure. Yeah, we've got some for lined up for the next couple of months beyond the summer. But yeah, if anybody would like to come on, please do get in touch. You can contact us through the website, AIoTHub.co.uk, and we'd love to have you sharing. And on that, we have Pete joining us, our good friend. Hi, Pete. How are you doing?
Yeah, not bad.
What have you been up to, my friend?
Partway through that, it looked like the internet. Oh, I think there's a lag. Partway through that, the internet went a bit slow. So I'm not quite sure what is going on, but we appear to be laggy. Either way, I'm very good. Thank you very much. You?
Very good. Full of busy, as always. Enjoyed a nice week off last week to get used to having a puppy in the house, which was a nice experience. Yeah, wasn't as hot as I thought it was going to be. And also, talking about IoT and throwing that in, I went to see Tool, a band in Birmingham the other week, and their stage show was phenomenal. I was really intrigued by the amount of kit and stuff that they had there, and started to really think about how you could really drive a different level of engagement with shows like that. Which, funny enough, I met with Formula One and Sky Sports and Live Golf over the past few weeks at a few events. I was at a great event called hosted by Sportsloft, who do absolutely awesome events. Check out their website. And it was really interesting with this whole AI push that's going on at the moment, how the whole user and customer engagement, and especially around like sports and entertainment and stuff, are really looking to push and adopt to create something sticky and interactive with them. So I think on that side of things, I think the whole edge compute, AI and stuff like that, there's an awful lot of exciting stuff starting to come through. And we've already seen it with Formula One TV. I don't know if you watch that, but just having that telemetry data and actually really seeing the intricacies of the sport, and imagine having that more tailored to you as a subscriber, I think could be a super interesting thing.
Yeah, I think McLaren have an enormous IT department, so maybe you can get an IoT speaker from there one month.
Do you know what? You've just I'm going to send an email whilst Pete's talking to a new friend I have at Formula One. Let's see if we can get them on.
Okay. If Pete unfreezes, Pete looks a little frozen there.
He does.
Oh dear! I don't think we've sacrificed enough goats to the demo gods here. He's unfrozen. Pete is back in the room.
I think Pete's lit the candle underneath the boiler to try and get the internet speed working.
The gerbils are running furiously, ladies and gentlemen. Broadcasting live from a hotel room in Birmingham because he's at a conference tomorrow.
Pete, can you hear us?
AIoTHub calling Peter.
Hi, Samuel. We've got Samuel online from Ghana. Nice to have you.
Welcome from Ghana. When Pete finally unfreezes, he'll be able to tell us how he bought a new TV today just for this demo because his Raspberry Pi wouldn't connect. So he had to get a screen working. Oh,
I think Pete's refreshing there.
Anyone know any IoT jokes?
I don't actually know any IoT jokes. Do you know?
No, I don't. I think I should do the scour of the internet to see if we can. Hello, Peter in Gateshead.
Sunny Gateshead. Hello, Peter. Just down the road from me. Nice.
Hello,
to have
Adrian.
You online.
Yes, we are monitoring your comments.
We have
back in the room.
Hello,
back
Pete.
in the room.
Yeah, so something went wrong there. I don't know what went wrong. But you were like Daleks, and I was then disconnected unceremoniously. So apologies for that.
Okay.
No problem, my
Not
friend.
bad. Looks like the lag's gone. And everything.
I'm crossing everything now.
Yes. Yeah. I kind of need the internet for this talk as well. So
Well, I mean, it is the Internet of Things, so
Yeah, otherwise it'd just be odd things and that'd be boring.
do you want to share your screen? Do you want to share your screen there, Pete? And
Yeah,
we'll,
let's do
Yeah,
that then.
we should let you get on with it whilst we've got
Yeah.
a fair wind.
Yeah, I agree with that.
we've got Andrew from Leeds. Thanks,
Oh,
Andrew. Great to have you online.
Leeds rules,
There we go.
unless
So-
it's Nottingham, Newcastle.
Nottingham rules. I agree.
Oh yes, please, Adrian, get in contact.
So can you see my
LinkedIn,
screen?
LinkedIn is
Yeah.
good. for me.
Adrian, find us on LinkedIn, AIoTHub, or you can find me. My name's somewhere. Paul Wheels, WEA.
We're always interested in interesting IoT stories.
Okay, we've got Pete. Pete, we've got your screen. I'm going to disappear and let you talk.
Okay, cool. I like the sound of it. Thanks, folks, for coming along to this. So just before we get going, I'm sat in a hotel room in Birmingham prior to going to the Smart Engineering, Smart Manufacturing show at the NEC tomorrow. Normally, I would be at home in the comfort of my own chair and a half-decent internet connection. But instead, I'm using my hotspot to control everything that you'll see in this whole demo. And there's a fair amount of moving parts. It all requires everything to work. So there's lots of crossed fingers. And when I got down to the hotel, the Raspberry Pi didn't connect to my hotspot automatically. Normally what I do is I plug that Raspberry Pi into the screen in a hotel room if I have to do that. Only there's no HDMI port on this TV. So I had to go and buy a television from a charity shop so that I could get my Raspberry Pi set up. Normally what I'd do is I'd bring a little tiny HDMI screen, but I didn't bring that stupidly. So yeah. Oh, well, we've got a new TV for the kitchen now. So that's all good. So this talk is about how we can build a Raspberry Pi driven robot arm, and we can use .NET 8, Blazor, SignalR, and a whole heap of other stuff, actually. So a little bit about me first. So I'm actually that one's updating now because I'm an application architect manager at Avanade UK. I was running my own IoT consultancy for the last sort of 12 years before joining Avanade. But now I'm doing all sorts of crazy stuff at Avanade, from sort of investment banking all the way through to helping big oil companies. So yeah, it's cool stuff. The color of my hair will tell you I've been doing this for many years. And in fact, I've been doing IoT since before there was an IoT, doing machine-to-machine type arrangements with stamp book dispensing machines for the Royal Mail and things like that. I'm also a STEM ambassador and a code club organizer, although the code club is dormant, so I'm not doing that at the minute. And I've got 2 little girls, which is the reason why I do all of this sort of stuff. So what are we going to be doing today? We're going to be talking first about .NET 8 and how we can get that onto a Raspberry Pi. And then we'll delve into Raspberry Pi GPIO and then the circuit that we'll be using. Then we'll be doing what is the hello world of IoT and flashing an LED and reading a button. And then we'll talk about device bindings and servos and things like that before moving on to Blazor and SignalR, so how we can make this all real time. And then we'll have some final demos and surprise bits at the end. So .NET 8, really it's a framework that allows you to be able to deploy anywhere now these days, from IoT, which is useful for us on the left-hand side, all the way through desktop, mobile, and AI at the far right-hand corner. So it's ubiquitous, and I love it. And I've been using it since it first came out way back in the early 2000s. So and that's going to power everything that you see in these demos today. What's new in .NET 8? Actually, .NET 8 kind of feels like a progression, an improvement rather than a whole heap of new stuff. But we do get .NET Aspire, which is an opinionated framework for deploying applications to the cloud. If you've not checked that out, then that's worth having a look at. And onwards from that, we've got some improvements and enhancements to JSON and ARM64 and the garbage collector, and we get some improvements for MAUI and ASP.NET and Entity Framework. And we're also able to publish direct to a container, which is useful. And interestingly, I learned that you can do that without Docker installed on your machine even, which I thought was quite a powerful addition. The .NET ecosystem itself, this is an old slide now, but really the one I want to call your attention to from my point of view is that bottom right-hand corner, 40% new to .NET are students. which I think is super important because obviously we know that Python is well used in colleges and universities, but to get .NET in there is important because we need these folks to be learning it at that point and taking it into industry with them. Otherwise, the whole thing just dies. So I think that's really important. I like that. So to get .NET installed on a Raspberry Pi is not as straightforward as you'd imagine. There's quite a lot of different commands that you need to be able to run in Linux and understand what you're doing. And I did that a few times and then got very bored very quickly. So I created a single line install script. And now this is the 8th iteration of this all the way through to the original version of .NET Core. So you can just run that single line install script and then I'll start mining Bitcoin on your Raspberry Pi. No, I'm kidding. But it raises the point of always make sure that you check what these scripts do. By all means, check what it does before. But you can see in that GIF that you run that, you reboot, and you've got access to .NET, the full version of .NET Core, essentially, .NET 8 in this case, on your Raspberry Pi, which is nice. It's worth bearing in mind, none of this works on a Raspberry Pi 5 at the moment because, well, I say none of it. Anything GPIO, anything that you need to control inputs and outputs, aside from maybe turning an LED on and reading a button, because they changed the architecture and it hasn't been updated yet. All of these libraries haven't been updated yet for the Pi to work with that yet. I started working on it, but ran out of time. So hopefully we'll have something for the Raspberry Pi 5 soon. So Raspberry Pi 4 and 3, I would say. And a 0W, I think, will work as well. So GPIO. Now, to get GPIO working, now GPIO stands for General Purpose Input Output, and that is all of the pins on the side of the Pi, which I'll show you in a minute. We use a library for this, a NuGet package, system.device.gpio, and that supports general I/O, like I've just mentioned, LEDs and buttons, but it also supports interfaces like SPI, a serial peripheral interface, and PWM, pulse width modulation, which we'll talk about shortly, and I2C and things like that to be able to connect other components to your Raspberry Pi and do things like, expand the I/O or temperature and humidity, God forbid. It actually supports other boards as well, like BeagleBoard, Hummingboard, Odroid, but don't even bother with those, just stick with the Raspberry Pi. It also supports, now leave this bit in here, even though this thing's dead, people still remember it, Windows 10 IoT, and this isn't the enterprise Windows 10 IoT. This is Microsoft's attempt to make a Linux variety that you could deploy WPF to, essentially. And it supported that, but that itself is dead. So don't try and use Windows 10 IoT. It's just a dead cause. If you want to make pretty apps, use Uno platform, and you can deploy that to, well, it's like a skier bridge, GTK. You can deploy that to a Raspberry Pi and get that working. So that's quite cool. And as I mentioned before, we've got very limited support for Raspberry Pi 5 with just the basic turn a pin on and off and read it. And that's as far as I got with that. So by all means, try, but you won't get very far. GPIO I mentioned before, general purpose input output, and that's these pins on the side of the Pi. Now we can see some important things to notice here is that we've got two different numbering schemes. So you can see these numbers close to the pins here. They're board numbering scheme, as it's called. Now I can do this because that square yellowy orange pin, that's pin 1. And then adjacent to that is pin 2, and below that 3, 4, 5. So I can count. But you could also use the BCM numbering scheme, which refers to the BCM chip and the numbering through there. Now that can be useful depending on what you're doing, but for the most part, just use the board numbering scheme. And this is important. You will see that in the code later. But again, you can see that we've got things like power there and transmit and receive and PWM. So each of these pins has got more than one function, nearly always. And we can control those and set them up in code. So hello world, if you're into IoT, we will flash an LED and we will read a button. That is generally the way that we test to see whether or not, A, we can hook components up in the right manner to our Raspberry Pi, but also that we've got the necessary software requirements all up and running on the Pi. So over here, if we zoom in, we've got on pin 10, we've got one side of a resistor connected to an LED, and the other side of it is just ground. So that's making that part of the circuit. So we can turn pin 10 on and off, and we'll flash the LED. And then over here, we've got pin 26 connected to one side of a button, and then the other side of the button is connected to ground. So that's that part of the circuit. You'll notice that there's no resistor connected to the button. So if you know a bit about electronics, you'd imagine that you'd need a pull-up or pull-down resistor for the button, but actually we can configure the Raspberry Pi to have internal weak pull-ups. It causes some interesting logic if you've not done this before, which I'll explain in a bit in how that the button works, but you'll see that shortly. So let's do Hello World. So this is the code, and I'll zoom in a little bit and shout if that is too small still, but I think that should be just about okay. Now, we're not doing much here. I mean, we've only got 38 lines of code, and some of those are curly braces. So we're bringing in some using statements here, and we've got that system.device.GPIO. Let me just get a zoom it up, and then we can zoom in a little bit better as well. So we've got that system.device.GPIO NuGet package that I mentioned earlier. So that's what we're using to do the heavy lifting of most of what these demos are doing, at least in the early stages. Onwards from that, we do a console.write line when we first start this thing up. Now, it does seem a little bit silly, but actually for the next demo, you'll see why it's quite useful in that this is a Raspberry Pi. It's not, a super fast gaming laptop or something like that. So it takes a while to build. Not an enormously long time. It's a Raspberry Pi 4, so it's reasonably powerful. But it does wait a while, and you don't know what it's doing. So at least if you put a Hello World in there, you've started. So it just helps for showing what's going on. The next thing we do is we start up this GPIO controller here. So that is allowing us to interface to the pins on the side of the Raspberry Pi there. And you'll notice over on the right-hand side of this that we've got that board numbering scheme. So again, we can specify BCM if we like, but we'll be using that pin numbering scheme of board. So everything will be matching those annotations that I put on the diagrams earlier. The next thing we do is we set the pin we're going to control, so the LED we're going to flash, to 10. So that's that pin 10. And if we go back here to the slides, you'll see that's that pin 10 connected to the LED. Next up, we've got this light time that we use in this thread.sleep down here. Now, this is there because if we try turning the LED on and off immediately, we're just going to get a slightly dim LED. So we need to give it time to be able to turn on and off and us actually use our eyes to be able to see it. So we've got a 300 millisecond delay. That's what that 300 means in between turning the LED on, which is what we're doing here with this controller.write. And we're telling it to use that pin, which is 10. And then we're giving it a pin value of high, on in this case. And then we wait. And then we have another controller.write with the pin, and we send it low to turn it back off again, and then we wait. And all of that lot is within a while loop. And so it's just going to flash on and off and on and off until we tell it to stop. And then at the end, when we've finally finished, we actually close that pin just because you should really. You'll see I stopped doing that later, but this is really just to show you best practice. Because releasing those pins in the case of things like servos can be quite important. So let's see if that works, shall we? Now, if I go .NET and run, this is just a .NET application, so we can just do that. And while that's waiting, you'll see it takes a little while. If I go to the next screen, then you should be able to see, and this is live, look. Woo. So no cheating, no magic. We should be able to see, if this all works, a flashing LED. So, yeah, that kind of gives you an idea about what that looks like as far as flashing an LED is concerned. But actually, this is a pretty important moment because we've proven that we've got the wires correctly connected to our Raspberry Pi, and we've got .NET Framework installed correctly, and all of our code is set up correctly to run, and we're able to control an LED. So I like that. But we're not quite complete, of course, because we need to make sure we can read as well as write to outputs. Now, I'm not going to do any coding in this whatsoever. I'm just going to switch between branches because I'm nowhere near brave enough to code while I'm doing this. So I can switch to the read branch, and you see now this is updated. Now, everything at the top is the same. But what has changed is we've now got a button pin, and that's set to 26. So again, if you remember the slides, pin 26 is connected to one side of a button. And then we open the LED pin as an output, and then we open the button pin as an input pull-up. So this is that internal pull-up resistor that we're activating for that pin. Now, if you don't do this and you forget to put an external resistor on, then the button value's floating around, and it may work today, and then it'll slightly get warmer and it'll stop working, or slightly colder. So if it's doing funny things, not working properly, check you've done this. Make sure that you've got some form of pull up or pull down, in this case a pull up, to a known value. And then what happens in our case is that on this pin 26, this is going to get pulled up to a 5 volts, well, 3.3 volts in this case, actually. So when it's not doing anything, it's going to be at 3.3 volts. Now, that's actually a high value. Makes sense, yeah? When I press the button, I'm going to connect this circuit down to ground. So that pin will become 0 volts at that point. So it'll be low. So the logic will actually be backwards, that we can see in the code. So in this while loop that I've got here, we can see that we've got a controller.read and the button pin. And if the button is false, so it's low, then we turn the LED on. So this is backwards, as I say. It kind of feels backwards, but with that explanation, hopefully that makes some sense. And if we're not pressing the button, so it's high, it's been pulled high, then we turn the LED off. And then afterwards, we just close that pin, so that piece of code hasn't changed. So let's run that one. Now you can see here that this is why I've left that hello world in there, because we're not ready to read the button. So you could go furiously pressing your button and it's not working. You stop the code, wonder why it's not working for an hour, and then realize it just wasn't ready. So now we can tell it's ready. And assuming that none of the wires have fallen out on my train journey down here, I should be able to press this button and we get an LED. And that goes, so there we go. Woo. We have a very, very expensive way to connect a button to an LED. With like 60 quid's worth of Raspberry Pi in between and a bunch of talking. So good. So that has proven at this point that we've got control over our Raspberry Pi and its GPIO. And we should be happy at that point, because actually that's a reasonable step we've taken. So let's move on. Hello world. The next thing we need to do is figure out how we're going to control the servos, as they're called. So servos are like little motors in our robot arm, and you can see our robot arm on that screen just here. So this is the robot arm that we'll be controlling, and actually there's a second robot arm in behind that I'll talk about shortly. But yeah, this robot arm and these blue things that you can see here are servos, and I'll talk about how they're working in a second. But it's not quite as straightforward as you'd imagine to control one of these servos. So we need somebody else's code to be able to do that. And that somebody else's code is the IoT.device.bindings NuGet package. And that somebody else's code is a whole heap of code that actually allows us to interface to a bunch of well-known peripherals and components, including, and if you ever have a conversation with myself and Cliff Aegis, we will start with temperature and humidity and immediately make retching sounds, because every IoT demo after what we've just shown you is a BME 280 temperature and humidity sensor, and it makes for a really poor IoT demo, because now you're having to blow on this temperature sensor and hope that the readings change and wait for them, and it's boring. So there's far more interesting things to do with IoT. Hopefully I'll show you that today. Onwards from that, there's things like the MCP23X series of I/O expanders. So we've only got a certain limited number of pins on our Raspberry Pi. If you need more, then you can plug a chip in, control it with SPI or I2C, and you've got access to as many of those as you want then, and you can go ahead and control a bunch of stuff with GPIO. There are a bunch of things called HATs, hardware attached on top. I should really capitalize that HAT because it's an acronym. And the Explorer hat and the Sense hat are two examples of that. Now, the Sense hat is a really interesting one because there's two of those and two Raspberry Pi 4s on the space station. Tim Peake took up the original Raspberry Pi 3s and the original Sense hat V1s up there when he went up. And then relatively recently, they got upgraded to Pi 4s and Sense hat 2s. And what that allows folks to do and specifically young adults and children, is join what's called the AstroPi project. And you can create some code and run it on the space station, which is mega. If you want to, light up a kid's eyes about doing this sort of stuff, tell them that they can run it in space, near Earth orbit space, but still space. Well, I mean, any person, I love it. I think it's a great idea to get folks into IoT and programming and stuff like that. Onwards from that, it allows us to move servos, which is important for us. Now, the circuit that we've got has grown, and I've used a sort of a driver board for the servos, but it's a raw driver. Now we'll talk more about how we drive servos in a second, but you can sort of see that in the middle of this. Now start zooming in. The top left is this driver board. It's called a Servo 6 board, and really all it does is splits out the control signals for controlling the servos from the power. And you can just do this yourself. And in fact, that's what I've done for the other robot arm, and you'll see that shortly. And you can see on the far right-hand side of this diagram, we've got a bunch of stuff connected here. Now, the first one is ground. Now, if you do buy this Servo 6 board, I made the mistake of missing the fact that ground label is off to the side, and I connected my first servo pin to the first pin, and it didn't work, and it took me a little minute to spot that. So first pin is ground. The next one is pin 35. Now, the Raspberry Pi has got two what's called PWM ports, and I'll talk about PWM shortly. But you'll notice that I've actually got 3 wires connected here. So one of them is on pin 35, and that's the hardware PWM port. And then on pin 13, another hardware PWM port. And then from there on pin 12, we've got another pin connected. And this is actually a software PWM port. And we get that courtesy of that same IoT device bindings NuGet package. And I'll dive into that in a second. I've been talking for a long time. John and Paul, are you still there? Am I talking to myself? Is it all still working? Hopefully, yeah, it is. Otherwise, that would have been a long time.
All good, Peter.
Good. Happy days.
I have to say there are a lot of additional devices on the device bindings namespace.
Oh, yes.
Everything you can think of. I'd recommend having a peruse, but have a look at that before you go buying some hardware from Pi Moroni. Otherwise, you might be wasting your money.
Yeah, well, it's never wasting your money from Pi Moroni because it's always fun. But John's absolutely right. And there's a link in my slides at the end to the list of all of those devices. And there are lots of them. It's really cool. Somebody's done a lot of work. So yeah, thanks for that, John. Appreciate it. I'll carry on. So on the other side of this Servo 6 board, we connect our servos, our little motors. So zooming in, on the far left is the control pin. And this is actually what's doing the movement of the servo. And then after that, you get the power and ground. Now, I've got yellow labeled on the far left of my diagram here for the servo. You might find that it's orange or a color like that. And it might not be red and black. It might be red and brown, but you can't really blow this thing up. You'll notice, red and brown, red and black, try and put those where the plus and the minus are, and then try and put the control where the control wire is, and you should be off and running. If you plug it in the wrong way, it just won't work. I'm not going to do any harm. So servos, what are servos and how do they work? So we use something called pulse width modulation. Now, what servos do is they kind of float in a position based on a frequency that you pump into that control signal wire that I was talking about there. Now, this is a little bit simplified, but the idea nonetheless is correct. If you apply a small narrow pulse and a large gap in between, then the servo will go one way. If you apply a slightly bigger pulse and a slightly smaller gap in between, it'll go to the middle. And then if you go with a big fat pulse and a small gap in between, then it will go to the right. It's really a lie. When you look at this on an oscilloscope, the pulses just get slightly bigger with a huge gap in between. So it's not quite like that. Really what you're doing is you're modulating the width of your pulse. Small pulse goes one way, large pulse goes another way. Now, these servo motors that I'm using here at least are 180 degrees of freedom. And they're really cheap ones. They're called 9G servos or 10G servos. And you just get them off of Amazon. And they're like £5 for a pack of 10 or something like that. So you can afford to just, ruin them and buy another pack. So both of these robot arms that we've got here, they're both using these same types of servos. Now, if you spend a little bit more and get the ones with metal bearings, then you'll have a better experience, but they are a bit more expensive, but not horrendous. And actually in the base of my main robot arm, I'm using one of those because I found it was jittery otherwise. So pay a bit more, get a bit of better value. So let's move some servos, shall we? So we return to VS Code, make sure that the demo is stopped, and then we can switch to the move servo branch, move servos, and then I'll run through the code and explain that again. Don't worry about the red squigglies. So if I zoom in a bit here, so we've got almost the same using statements, only now we've added system.device.pwm and system.device.pwm drivers and IoT.device.servo motors. So this system.device.pwm is actually what's doing the low-level control of the servo motor. So that's giving us access to the pulse width modulation, the PWM ports on the Pi. And then the IoT.device.servo motor, that's coming from the bindings. So somebody else's code that's actually changing or using code to make it easier for us to worry about those pulse widths and how you go about setting the thing up. All we want is to just tell it what angle to go to, and we're off and running. So that's kind of what we want to do. So downwards from here, we've still got our hello world that we had before, but now we're standing up a bunch of PWM pins and channels. So we create a PWM channel 1, and we pass in some bits. So this first number here is the chip number of the PWM device. Now there's only one chip, and this is 0 based. So both of these you'll see are 0. And then we've got which hardware port, and there are 2 hardware ports on the Pi, so 0 and 1. And then we pass in the duty cycle, and you don't need to worry, just leave that at 50 and off you go. So this is using the IoT.device NuGet package. But this is, well, not the device bindings. I mean, this is the GPIO package rather. And then this part here is using the IoT.device bindings library to do the servo motor side. So we can create a new servo motor. We can pass in our PWM channel. We can tell it the degrees of freedom that we've got. And again, 180 degrees for this, because otherwise all the wires will get tangled up. And then we can tell it the minimum and maximum pulse width. And this is all about figuring out where the end stops are on our servos. And you can pretty much just leave those at the value there. And if you start needing to figure out a better way of doing it, by all means, you can fiddle with those figures and see what you can get it to do. So we've got 2 of these PWM channels, one for each of the hardware PWM channels on the Pi. And then we create a software PWM channel, because we've got 3 servos I need to move, but only 2 hardware PWM channels. But again, this IoT device bindings library gives us a software PWM channel. Now, we're talking about really fast pulses here. So it's really important that you make sure you add this true on the end. Now, what that does is it kind of skips out some of the operating system layers and goes direct to the bare metal almost to do some really fast timing to get this to work, to get the software PWM to work. It took me a while to actually figure that out, and somebody from the IoT team put me onto it and solved a load of my problems. But to get this software PWM channel, we pass in the pin of the Pi that we want to connect the servo to, 27 in this case. That same duty cycle. I forget what that 0.5 actually is, but don't worry too much about that. Just leave it as it is. And then everything else after that is identical. So we create a servo motor, pass in our PWM channel, tell it 180 degrees, and then I changed these ever so slightly just to kind of work around the fact that this is software and the timings weren't quite right. And then next up, we've got a servo motor start set of routines. So we start our 3 servo motors, and you'll notice when we run the code, it kind of jerks a little bit and it engages the servos and it sits at an angle. And remember, these servos are floating, so they're actually getting their PWM signal at that point, and they lock into place. So next up, what we're going to do is make our robot arm dance. So I've got a little routine down here called move to angle, and it's really just to simplify the code a little bit. And in it, we've got the servo that I pass in. So I pass a servo motor in, and I tell it to write to an angle, and the angle I pass in is the angle that it gets written to. So I do that a bunch of times up here. So servo motor 1 will go to an angle of 70 degrees, and then servo motor 2 will go to an angle of 20, and then 3 to 80, and then 150, 50, and 150. And so we should see our robot arm doing a dance, essentially, and it'll just do that over and over again. And then at the end, I stop these servo motors, and then we've got control over those pins again, should we want. But more importantly, it shuts the robot up, because if it gets in a little bit of a funny sort of angle, it can jitter. And in fact, that's what the other black robot arm's doing at the moment. This whole time it's been jittering, but that will stop in the not too distant future. So let's see what that looks like. Let's run that. And again, no code, or at least no coding to do, and only 74 lines of code in this whole part of the demo. So not too bad, really. But when that starts up, all being well, here we go. So we have a dancing robot arm. So that was the reach, and that's the grab, and then that's the rotate. It's going to hit the other robot arm, reach, grab, and rotate back again. So there's 3 servos that I've named: reach, rotate, and grab. The rotate one you can't see because it's in the base of this little section here. But you can see the reach one and the grab one just there, and they're connected down to the Servo 6 board, and then on through those wires down to that Raspberry Pi. But actually, this is pretty cool, because in almost no time at all, 37 minutes plus stoppage time, we've got a robot arm moving in .NET, and that's pretty cool. And I could have just left it there like that, but that would be boring, wouldn't it? Really what we want is to be able to control our robot arm properly. So let's stop that code. There we are. You can stop, and let's go back to our slides. So the next thing we need to talk about is Blazor. Now, if you ever talk to me or come and watch some of my earlier talks that aren't this one, you'll hear me talking about things like IoTHub, and obviously from this you'll hear about things like IoT operations, where we can send data to and from the edge. But what it's not very good at when you do that is real-time control. So what I wanted was the ability to be able to move my robot arm at will in any way I wanted, immediately, in real time. And so creating a website was the way to do that. And Blazor is the Microsoft way to do that now, which is nice. So it's been around for a little while, but really it's a single-page app framework for building interactive client-side web apps with .NET. So if you've not used it before, then it's a SPA framework, but we're using .NET everywhere. So although you can still use JavaScript, it replaces all of the JavaScript with .NET and runs that as WASM, if you like, in the browser, which is pretty cool. It was actually a pet project by this Brit on the right-hand side, Steve Sanderson. He took it to a Microsoft demo, demoed it, and everybody went, "Oh, my brain's just exploded. We need to put some effort into this." And then they did. And now it's everywhere. And onwards from that, there are other frameworks like Maui that we'll talk about shortly. So yeah, all C# and Razor and HTML, so no JavaScript, which is nice. Although, you can't do everything. So sometimes you've still got to drop into JavaScript, but that's becoming more and more rare. There's a bunch of different ways of deploying Blazor, different flavors, if you will. There's server side. And so what this does is this spins up a server side application, and what you get is a thin client in the browser. And actually using SignalR WebSockets, the DOM changes are actually communicated down to your browser, but all of your code actually lives in the cloud, which can have some benefits in that it's quite good for keeping your code private. So your JavaScript isn't on the client anymore. It's your .NET code that's replaced it is just running in Azure or wherever you deploy it to. The other option for that there's a few, but the other option for this now is client-side WebAssembly. So what this does is, in essence, creates a virtual machine in the browser, and it runs .NET Framework in there. And you actually get the full .NET packages arriving on your machine, and they run from there. So I don't think they're quite at bytecode WebAssembly yet, so it's still running the full code, but it's pretty powerful actually. Important to note that this is not Silverlight. Sorry, Silverlight. This isn't Flash or anything like that. There's no plugins needed for this. This just runs. This is just HTML, so off it goes. And it's supported, at least it was last time I looked, but goodness knows what Safari's doing today. It's supported in all modern browsers, so you should be good to go with anywhere you want to go. You can read a bit more in that bit.ly if you like about Blazor. Onwards from that, we need a way to be able to communicate between our web app, in this case, and our Raspberry Pi. And to do that, we can use something called SignalR. Now, SignalR is a library for ASP.NET developers to add real-time web functionality to their applications. And really, if you've done any SignalR and you've done any of the tutorials, you'll be making a chat app. And really, that's what I've usurped for this demo, really, just to keep it as simple as possible. But the premises are the same. So this has been around for a long time. So Damien Edwards and David Fowler, two fantastic folks. That was from NDC Sydney, that photo I took there. They created it way back in 2011. So this thing has been around for ages. And it enables bidirectional real-time communications, which was important for the way I wanted to make this demo work. On the top level, it supports WebSockets, but if you can't get WebSockets to work because of networking reasons, then it will automatically drop down to things like server sent events and long polling and things like that. So it should just work no matter where you put it. And beautifully, it's open source as well, so you can contribute to it should you want to. So let's drive the ARM. So if we go across to the code, I am going to fast forward now all the way to the very end of the code. Boom, boom, boom. And to main. Do, 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 do. And we can go, and there we are. So this is our code. Now, I'm not going to show you all of the web code, but actually all of the web code is pretty similar to what you can see in here. So I'll explain the code that's in here. And all of this code is all open source, and you can feel free to go and check the code out yourself. But we've got so much more that I want to do that sitting around looking at the web code is not all that interesting. So what I'm going to actually do is I'm going to run this first, and then I'm going to show it running and move it around, and then I'll come back and explain the code. So my code is actually running here. So if I full screen that, it's going to be a bit easier. And then I zoom in a little bit as well. There we go. So this is running here, and this is live. Woo, there's my hand. So that should be all up and running. And if I rotate my arm, no, it's not up and running yet. It's not there. It might be there. I'll tell you what I need to do. Because it's SignalR and it's WebAssembly, we need a live connection. And after a while, that connection breaks. And the demo's been going for long enough now that it broke. So it's not broken now. So I should be able to reach my robot arm. So there we are. So that reaches forwards and backwards. You can see in the background there that the other robot arm is doing this. Now, this is .NET Nano framework and on a very low-powered ESP32. And so what it doesn't like is lots and lots and lots of messages, which is exactly what I've just given it by moving the arm in that way. So if I click, though, then that moves. It's still quite slow, but I think maybe the batteries are running low. There we are. There you are. You can sort of see it in the background, just getting a bit busy. The other one, it's happy. It's happily moving. And then we can control the grab as well. So you can see that grabbing forwards and backwards. So we've got 3 sliders here, and each of those are sending essentially chat messages down to from this website, this Blazor website, down to our Raspberry Pi. So let's have a look at the code for that. So zoom in again. At the top up here, this is pretty much all the same So we've got our servo motors and the drivers, PWM and all of that lot. But now what we've done is added HTTP, because we'll need that, and SignalR. So that's the two main things we're going to need. And we connect a hub, we create a hub connection, which is our SignalR hub. And then we do our hello world. So that's all the same. All of this PWM stuff is all the same as well. But next up, we connect our SignalR hub. So we create, using the hub connection builder, a new connection. And we add the URL, and that's the URL I happen to be connecting to. And then there's this section here. Now, this is actually, doesn't need to be here for the web version of this. If you want to run this locally, and you're going to connect from your Raspberry Pi to your PC, it's easier just to tell it to dangerously accept any certificate than it is to try and set certificate authentication between your machine and the Raspberry Pi. I got bored trying to make it work, and so I just did that because it took away from the demo. So that's what that's doing. We also tell it to automatically reconnect in case I'm on a hotspot and it decides to disconnect. And then we build that connection. So really this section here is all about connecting to our SignalR hub in the cloud. Next up, I've got a little handler here so that when I do a Control and C, it actually disconnects everything, stops the motors, and exits the application, because now we're running in kind of a thread within this connection. So we need to do this properly. Then, and again, if you've done the SignalR and you've done a demo, you'll have done a chat app, and you'll see that that's what I'm mirroring here. So from our connection, we can hook up a handler, so an on, for a particular type of message, and receive message is the one that I'm using here. And we tell it we're going to accept two strings, and those two strings are called user and message. So this would be, you know, Pete is the user and hello would be the message. But in our case, we're going to send the servo as the user, and we're going to send the value that we want that servo to move to as the message. So I've done this on purpose so that you can see the number of steps away from just a tutorial on SignalR is not far from where we are. You can use that exact same code, usurp it, change it around just ever so slightly, and now we've got the ability to remote control a robot. So we've got servo 1, servo 2, and servo 3. We're just using our same move to angle, and then down here you'll see that hasn't changed either. So we're able to receive those SignalR messages from the website, and they come down to the Raspberry Pi, and you can see those in the bottom left-hand corner here. So that value 108 posted by servo 3 in that case, which I think is grab, and that will go ahead and move around the servos and the robot arm essentially. So not too many lines. What are we on? 115 lines of code there, and there's some spaces. So not many lines of code to get Raspberry Pi up and running with .NET. Now I could have stopped there as well if I wanted to, but that would have been boring as well, and I don't like that idea. So let's go back to the slides and introduce Unity. When I was doing this, I thought, how cool would it be if I could take a Quest, in this case a Quest 3, and actually control my robot arm from in virtual reality, or in this case actually mixed reality. So I went ahead and did that. Now Unity is a cross-platform game engine, and it gives users the ability to create games and experiences in both 2D and 3D, or VR, as our case is. Again, this is old, 2002. This has been around. Cross-platform, as it just said, and we can script in .NET Standard 2 or C#8, so reasonably up-to-date stuff. Not mega up-to-date, but reasonably up-to-date stuff. So again, .NET, so we're .NET everywhere. We've got support for virtual and mixed reality, as I've just said. And with the Unity application up and running, we can deploy directly to a headset if we wish. It's worth bearing in mind that adding NuGet packages is really painful, even today, in that you've got to do a load of tree shaking. You've got to go and find the individual ARM NuGet packages sections, so the actual NuGet sections that are relevant to that, and find them all and copy them all in and register them manually. In my code base, you'll see that there's actually a script to let you do that. So you can use that script to figure out how you go about doing it, but it's pretty painful for some reason. I'm sure there must be a better way, but I didn't find it. So let's move it with Unity. To do this, I am going to leave my code running, which it is doing at the moment. And over here, we've got our robot arm. But actually, if I go ahead and go a little bit further, then there's a casting page here. So what I'm going to do is I'm going to put my headset on, and hopefully you can actually see me as well. But if you can't, then you'll see the cast in a second anyway. And I'm just going to start my application, this one here. So I'm starting, you won't see this at the minute, but I'm starting up my robot arm mixed reality application. Now, if I start streaming this to the computer and press next, all being well, good, that seems to be working. So if I full screen this so that you can see that a little bit better, then this is my hotel room, Pete's hotel room. But if I press resume and I move this over there a little bit, we've got a mixed reality robot. So we've got Inception happening on my laptop screen. We've got the real robot arms, forwards and backwards, done on Nano framework and the Raspberry Pi. And then we've got a mixed reality robot here as well. Now, this used to just be a VR demo, which was okay, but I couldn't actually see anything that was happening in real life. So when I got the Quest 3, I upgraded it to be mixed reality. I had to start the whole thing from scratch because my VR Unity project was so old that I couldn't upgrade it. So I started from scratch, which was interesting. But what it's given me is the ability to have a menu in here. And so in theory, I can rotate my robot arm from mixed reality here. So you can see that moving. And over there, you can also see a mixed reality robot arm moving around in there as well. So that's the reach and then the grab. You can see all of that lot moving and over there as well. And the very slow and will catch up eventually. .NET Nano Framework 1 working at the back as well. So yeah, that is pretty cool. And in actual fact, if you wanted to, because this is now on the web, if I go all the way back across here, if you want to scan that QR code there, then you too can control the robot arm from where you are. So I'll wait, and when the robot arm starts going absolutely crazy, then I'll know that somebody's at least dialed in. It'll be interesting to see whether or not that works. But when I first did this, a good friend had moved to New Zealand, and I gave this talk, and he dialed in from New Zealand, and he was able to control the somebody's in, look. Now, what I found is during my train travels, be careful, during my train travels, this black wire for the power had fallen out. And so it's really just kind of sitting in there. So if this robot arm stops moving, it's because that black wire has been pulled out. But, oh, look, they're throttling my robot. That's just rude. I'm going to move him out of the way so you can't damage poor little black robot over there. Look. So that's pretty cool. I like that. So I ask you to stop. If you are controlling the robot arm, please do stop because we've got more to talk about. Look at you not stopping. Thank you. Oh, rude. The rudeness is unbelievable. So I'm going to take this off my head. Oh, actually, I'll stop casting first because it's using up precious. There we are. Stop casting. Right. Which way around are we? Oh, so you've stopped. That's nice of you. And then we're over here. So yeah, that's all still working. And that stopped casting, which is good. Now, I mentioned earlier that this is deployed as a Blazor app to the web, which is great. Now, what's good about that is that the SignalR hub is in the web, so it's an accessible endpoint. So once you've done that, you can start connecting other things to your robot arm as well. So if I go ahead, we've got a bonus section. So if I go to here, we can create something called a Maui app. Now, I've not been forward planning enough to hook my phone up to my machine, but on my phone here is a Maui app. So what we can see is that in theory, I can move my robot arm Power of Maui on my mobile phone. And this code is almost identical to the Blazor code and almost identical then to the code on the Raspberry Pi. So I like that. It's pretty cool. We've got the mobile app version, but there's more. There's more, he says, because we also want to tick all of the boxes, don't we? And it's no good just doing mobile and Raspberry Pi and web. There's more. So if I click this down here, we have a Maui desktop app as well. So that's that same app on the right-hand side, at least, that you saw on mobile, where we can control our robot arm. So that rotates it. And then we can reach forwards and backwards and do all of those good things. That's exactly the same as we saw before. But even better, I can control it with my voice using the speech service in Azure. So let's see if this works. So rotate by -100. There, look. Me controlling a robot arm with my voice. Reach by 20. There. How cool is that? So, all the way back across here to my many different virtual desktops. Keep going. Come on, you can do it. All the way back. I told you there was lots of moving parts to this. On the next slide over here, we really have done all of these. So you've seen that on the Raspberry Pi, we've got an IoT.NET deployed down there. Then we've got the web version and cloud, because obviously those two things go hand in hand, but I've got a web app deployed to Azure. You saw the .NET MAUI desktop app and the .NET MAUI mobile app. And then with the Unity and Oculus MetaQuest headset, we've got the gaming side covered. And then with the .NET stuff for AI. I know it's not Gen AI, but who wants Gen AI on a robot arm, I ask you. But we can control it with our voice and .NET. So we really have ticked every single one of these boxes. So really, I've tricked you by watching a robot arm talk into really this is talk about .NET everywhere. And you really can deploy this anywhere you like, even to a TV if you like, to Tizen, Samsung TVs and stuff like that, but not something that I'm in a rush to do. So it wasn't as straightforward as you imagine. My sadly dearly departed cat now died recently, but she's the love of those servos. And this thing put that in because what you can see here is pretty cool. I mean, at least I think it's pretty cool. But it's not a work of a minute. This is, this talk's been around now for about 3 years, really, from like just a really basic robot arm control demo all the way through to everything that I've added to it now. So these things don't come fast, but actually the steps aren't that hard. You can see the code isn't that complicated. And that full set of source code to control the robot arm remotely really is only 116 plus blanks. It's not too bad, really. So I'll stop that now because that's just getting annoying. I'll turn off my other noisy nano framework robot arm. So that is that. There's a bunch of links here. There's the GitHub repo and workshop there, so you can actually run through a lot of this stuff yourself. All of the code, actually including the Unity stuff, but it's not in that same repo because it's too big. You'll find on my GitHub. There's a blog post there, that bit.ly .NET 8 Pi. That is a blog post on my website on how you can run through getting .NET 8 installed on your Pi and then start controlling some GPIO basics. The GPIO NuGet package is there. The .NET IoT device binding source code is there as well. If you go to that will have that list that John was referring to with all of these different devices that you can control with that NuGet package. It's awesome. The 3D printed robot arm from my presentation. So this one right here. There's a link for that, and there's a link for the one in behind as well, which is actually created by my good friend Cliff Aegis' son. That's actually a lot easier to build, that the black one, in that there's only like 4 parts or something, and you can print them all flat, and you screw the servos directly into those parts, whereas this one needs all sorts of nuts and bolts, and took me about an hour to build. And it's becoming slightly a bit like Trigger's broom, if you know that, in that I'm having to replace bits now because it's been around the world twice, literally. But it's good. It's fun stuff. And then there's a workshop down here for that as well, where you can get all of the parts lists and everything too. I think that Bitly will take you to the GitHub. If you need to contact me, you can contact me at lots of different places, but at Pete_codes on Twitter is the best way to do that. Send me a DM. I like them. You can email me at PJG Creations if you like, or look at my personal website. And then NotsIoT, I run, which is kind of like a version of this, but in Nottingham. And in fact, we've got a meetup on the 24th talking about IoT, on the 20th rather, talking about IoT operations. Christoph Cremon is coming along to talk about that. So poaching your viewers there, John and Paul, but I'm sure you don't mind. I also run .NET Knots and the dormant at the moment Knots Dev Workshop, and Lati, which is a Loughborough-based technology group. And I'm part of the Agile Engineering podcast, which we've not released anything in a little while now, and Azure-ish Live for the same thing. You don't need to worry about taking all that down. The slides are actually there. And in fact, there's a Bitly QR code there that you can scan, and that'll take you to the slides on SlideShare. And that is me done. So by all means, take that down, and I will stop sharing.
Excellent. Thank you very much, Pete. That's, as always, absolutely ridiculously entertaining. So thanks for that. Yeah. Love it. Love a good interactive one, right? That was brilliant. I hope I didn't break the robot much thing, because I was totally messing around with everything there.
Don't worry.
I was trying to work out how to try and do inappropriate arm movements whilst I was messing around there. But,
I need to turn it upside down, probably.
But that was absolutely brilliant. I do apologise. I need to rush off to have a nice call with my American colleagues. But
No
thanks, and by all means, always plug and use us to share your community, and vice versa. We'll share yours, right? That's what we're all about, working together as communities, mate. Absolutely fantastic. Thanks very much. And on the back of today's show, you've pulled in a great audience, by the way, my friends. So thanks very much for that.
Cool.
We've had a number of people get in touch about doing some talks in the near future as well. So there's some emails on the way and stuff on that one, John. Thank you very much to everybody for joining us. John, thanks so much for all your help as always. It's great doing a partnership with you on this. And on that, I shall say, as he's stalling to find the video, good night. Bye.